Perhaps I should add a comment or two about the partial trace. As you know, we introduced the partial trace as a way of associating density operators with subsystems. So when we have two subsystems or more, but let's say two, A and B, of course, and possibly entangled, then we know that the state vector formula doesn't quite work because entanglement excludes the possibility of associating state vectors with individual subsystems. But that's not the case with density operators, and that's why we are talking about density operators. That's why we introduce density operators. We want to be able to associate the quantum state with individual subsystem. And the way we do it is by reduction, and that reduction is done by the partial trace. So when we have two subsystems described by some density operator rho AB, we can associate density operators rho A and rho B with the subsystems by taking the partial trace, which is all for your convenience. I just provided you with the definition again. Now, you may ask, is this the only operation? After all, what it really does, it takes density operators, right, in that operate on the tensor product of the two Hilbert spaces associated with the two subsystems, and it generates density operator, say rho A. I can also take rho B, that acts on the Hilbert space associated with one of the subsystems. There are probably many maps of that kind, but the question is why picking up the partial trace? And the reason we pick up the partial trace is that we are forced to pick the partial trace because of the consistency of statistics. So of course, you know, we can, even though we are going to perform measurements on subsystem A, but we can, if we want to, we can use we can use for calculating statistical predictions the density operator of the whole system, in which case we simply just use the extended observable, say A tensor identity. So at this point, even though the observable A pertains to the subsystem A, we simply acknowledge that there's another subsystem B and tensor it with the identity. Identity doesn't do anything, it's just a lazy operator. It just simply says we are not touching B, we are doing operations on A, but we can operate in this tensor product Hilbert space and get all the statistics about the A. And for example, the average value of A in this case is going to be trace this extended observable times rho AB. But at the same time, when we associate the density operator with the individual subsystems, then needless to say, we want this density operator to give us all the statistics that are required for any measurements whatsoever associated with subsystem A. So we want this to be equal to trace A rho A. Now, this innocuous kind of relation, which seems to be pretty obvious, which is all about the consistencies of your description, that you know, I can derive all the statistics about the subsystems using the bigger density operator, but I don't have to. I can do the reduction. If I have the reduced density operator, I'm also fine. But there has to be consistency between those two tools, two mathematical approaches. So, and that has to be valid for all possible observable on A. For any Hermitian operator A must satisfy this relation. So if this is the case, so it turns out that this is actually quite a strong requirement. It may not look like this to you at the first glance, but it is. And I'm not going to derive the next step, of course, will be just to show that this implies, because it does imply, that the partial trace reduction. So that simply means that for this to be satisfied, you go from rho AB to rho A by the partial trace. So you have to use this this mathematical tool. The bottom line is the partial trace is the only operation that we can use in quantum theory to go from the density operators of big systems to subsystems.